This is C2, Core 2 and Chapter 9 on differentiation. So at the end of this booklet, we will be able to know the difference between an increasing and a decreasing function. Use differentiation to find a stationary point, and that's looking at the gradient of the tangent to a curve. Then be able to take those stationary points and see if they are a maximum, a minimum, or a point of inflection, and that's using the second derivative. Then taking all these facts from 1, 2 and 3 and apply them to exam questions to solve problems on differentiation. So maximum, minimum turning points, points of inflection, and real life problems of maximum and minimum, usually involved with volumes or surface area. Looking at a familiar curve, we have y equals x squared, and that's in the red here, so that's y equals x squared here. And what we want to do is look at when x is less than 0. So x less than 0 is if we go from along this axis here, we can say that y actually decreases as well. So for x less than 0, if we come from this side and go along to 0 in that direction, we can see that y goes from a value up here and down. So we can actually say that it is y decreases as x increases. And we can see that here as x increases, so getting towards the origin here, then y decreases as x decreases. And what we say here is that y is a decreasing function of x. Now if we look at the tangent to the curve at the left hand side here, we can see that this tangent to the curve actually has a negative gradient. That's what we're drawn in there. So a decreasing function actually has a negative gradient. So if we look at this part, so the gradient is negative when we've got a decreasing function. When x is greater than 0, so what we've just looked at was x less than 0. If we now look at x greater than 0 on the right hand side, we can see that as we move from the origin this time and outwards, as x increases, then so too does y. So this is called an increasing function. So for x greater than 0, y increases as x increases. And this is known as an increasing function. And it's fair to say then that the gradient is also positive. So if we look at the tangent to the curve that we have here, then you can see that this has got a positive. Now tangent to the curve is just your dy by dx, or your f dash of x. And we're going to make use of that when we look for increasing and decreasing function. When we have a stationary point, that's when the gradient is equal to 0. So we're looking for a horizontal line. If we look at the origin, you can see a stationary point here. So what I've got is a tangent to the curve y equals x squared. We have got a horizontal line, and that means that we have 0 gradient. So that's one of the key things that we're actually going to be using in this chapter. So at the origin, the stationary point, the gradient is 0. And we can put that into mathematical language. If you look just below at the bottom of the page, we have got lots of things, or 3 statements that we can actually stay here. So for an increasing function, so you have to know this part. So an increasing function, f dash of x is greater than 0. So that's the function notation. We can also say dy by dx is greater than 0. For a decreasing function, we saw the tangent to the curve was less than 0, it was negative, and that also means that dy by dx is less than 0. So remember, there's 2 different ways of representing differentiation, in the function notation and the Leibniz notation. And then the third one, which is really important, that we're going to use quite extensively, if you have got that keyword, stationary function, then dy by dx is actually equal to 0. You're not given these, and the keywords that are associated with it, you have got to memorise what it actually means. We've got to memorise these. Let's look at the first example. And we've got a cubic function here, given that y equals minus 7x plus 9x squared minus 2x cubed. Find the range of values of x for which y is an increasing function. So that statement there tells me that for an increasing function, dy by dx is greater than 0. So let's work out dy by dx first of all. Remember, it's multiplied by the power and then take 1 away from the power. And constants, because they're horizontal lines, when you differentiate a constant, it's 0. So we get 18x minus 6x squared. And because it's an increasing function, dy by dx is greater than 0. So what do we have? We have 18x minus 6x squared greater than 0. And what do we have? A quadratic inequality. And we take special measures with this, and we consider, because we have to get the critical values on the graph, so we consider 18x minus 6x squared equal to 0. If we factorise that, we can take out 6x, and that leaves us with 3 minus x equals 0. So it's going to cut the axis at x equals 0 and at x equals 3. The quadratic looks something like this. It's a minus x squared, so it goes in that direction. That's your x, your y, label your axes. So that's at 0 and that's at 3 there. And the part that we want is greater than 0. And greater than 0 is this part here, the part above. And when it involves the maximum or the minimum, it gets sandwiched in between. So therefore, x is in between 0 and 3. And that's why in the question it says find the range of values. So here's quadratic inequalities coming up again in C2, and it'll definitely come on in C1 as well. So we've got to be able to solve these with ease. Right, what I'd like you to do then, well, if we actually have a look on the next page, the first thing, if you just take a note, first of all, those are the questions I'd like you to do on the exercise. But what I've also done on the next page is I've drawn the graph of the cubic, and then you can actually see from 0, from x equals 0 to 3, we have got an increasing function. And that's to say that the gradient of the tangent to the curve throughout this part of the cubic is has a positive gradient. So that's what it actually means. So the questions that I'd like you to do, if you move down, there's two questions there, just the first column of each. And notice it's f dash of x in the first question, and we want it to be an increasing function. And then in part 2, it's y is a decreasing function, so it's finding dy by dx less than 0. So if you pause the video now, and then I will reveal the answers and you can mark your own work. I would say maybe 5-10 minutes on that, and then start the video again. Welcome back, and the questions that we have, if we look at the first ones, for an increasing function we make it greater than 0, so check A, C and E. For part C and E you have to draw the little diagram to find out the range of values. And then on question 2 we were looking at decreasing functions, so we're looking at dy by dx less than 0. Again, draw the quadratics when you get a quadratic inequality. And C was quite interesting because if you look at what we had here, the quadratic that you get will never actually be less than 0, so that's what it actually looks like. So it's not actually possible to find values that are less than 0, there's nothing below the axis. And you can confirm that by working out the discriminant, because if the discriminant is less than 0 then it doesn't cross the x-axis, so we can't get anything below the axis. So if you mark your own work, and then we'll get on to the next part. Stationary points then. This is a huge part of the differentiation, and if you look at what we have here, we've got a minus x quadratic first of all, then we've got a plus x squared quadratic for the second one. And what we want to find out is stationary points for these curves. So if we draw in the gradient of the tangent to the curve, and I'm hoping you can use a ruler and do it an awful lot straighter than that, at that point there, at the maximum turning point, we actually get f dash of x is equal to 0, or we can say dy by dx is equal to 0. So for any stationary point the gradient is 0, and for a maximum turning point the gradient just before is positive, and just afterwards, so the parts that I'm looking for, the gradient of the tangent to the curve is positive here and negative here. If we look at the second one, for a minimum turning point, again we've got stationary point dy by dx is equal to 0, or our f dash of x is equal to 0 for stationary point, so the gradient is 0, and at that point there we've got a minimum turning point. And you can see from this diagram on the left, just before the minimum turning point we've got a negative gradient, and just after the turning point we've got a positive gradient. Then we come on to points of inflection. Now these are quite unusual because although they will have a stationary point, you can see here it's a cubic, we'll have a stationary point going right through the middle here, so at this point dy by dx is equal to 0, and we've got dy by dx is equal to 0, or f dash of x is equal to 0, either of those notations depending on what you're given at the beginning. But you can see that the tangent to the curve on both here is a positive gradient and then a positive. So if the gradient doesn't actually change before and after the stationary point, what we've got is something that's called points of inflection. So this one here, if we look at the gradient just before the turning point and just after, we will see that we have a negative gradient and a negative gradient as well. And these are called points of inflection. And we'll come across the second derivative. We did the second derivative in C1, but we didn't really put it to use at all. We just did the mechanics of it. But this time, the second derivative will actually tell us if we've got a maximum or minimum point. And with points of inflection, you would get a d2y by dx squared is equal to 0. You can't actually say it's a point of inflection. It's pretty inconclusive. But if we look at the gradient just before and after the turning points, we can determine whether we do have a maximum minimum point or a turning point. So what do we have to remember from this or these graphs here? If we have dy by dx equals 0, we know it's a stationary point. And also, if the second derivative is negative or less than 0, then we get a maximum turning point. So these two things in conjunction will determine the nature. So it's either determining the nature or identifying the nature of the type of the stationary point. So stationary point can either be a maximum turning point, it can be a minimum turning point, or it can be a point of inflection. And we can use the second derivative to actually identify the nature or the type of these stationary points. So the second one we've got is stationary point dy by dx equals 0. If the second derivative at a point x that you've found is positive or greater than 0, we get a minimum turning point. And what I just said from the last diagram, we get dy by dx is equal to 0. If also the second derivative is 0, it's inconclusive. So what we have to do is look at the stationary point. So that's where dy by dx is equal to 0. And look just before it and just after it to see what the gradient is. Now, how do we apply this? Let's look at the example below. We have find the coordinates of the stationary point. So there's our key statement, stationary point, and that tells me that it's dy by dx is equal to 0, and we've been given the curve as well. The other thing that we could do here as well is actually determine the nature of the turning point. So I'm going to add this in as well. So determine the nature of this turning point. Now if you look at the equation, we've actually got a plus x, so a plus x squared. So we're expecting a happy quadratic. So we are actually expecting it to be a minimum turning point. So we wouldn't normally get it on quadratics, it's really cubics or quartics. But this is a simple example just to get you into the swing of what you should be doing. So if we have to also determine the nature, then we're going to have to look at d2y by dx squared. So let's first of all work out dy by dx is equal to 4x minus 12. And for stationary points, dy by dx is equal to 0. So that implies that 4x minus 12 is equal to 0. 4x is equal to 12, so x is equal to 3. If we put that into the original equation, y equals 2 times 3 squared minus 12 times 3. So the y coordinate with that is minus 18. So we've actually got a turning point at 3 minus 18. And to find out the nature, if we do d2y by dx squared, differentiate the first derivative, that is 4. So that's greater than 0. So that tells me there actually must be a minimum turning point. We're not asked to sketch it at all, but just to give you an idea of what it would look like. I'll go through 0, such and such, and that'll be the 0.3 minus 18. So it'll look like that. But as part of an exam question, you could possibly be asked to sketch a cubic or a quartic, finding the turning points, etc. Okay, on the next one then, find the coordinates of any stationary points that you've got on this curve. And we could determine their nature as well. We'll just go for, yeah, I think I'll add that as well. So what we'll say, and determine their nature. Okay, let's start off with. Right, so for stationary points, we need dy by dx is equal to 3 minus 3x squared. For stationary points, dy by dx is equal to 0. So that tells me that 3 minus 3x squared is equal to 0. Take a common factor of 1. And we've got dots. So if we do that, we've got 1 minus x, 1 plus x. So that means that we've got x can be equal to 1, or it could be equal to minus 1. So we've got two turning points there. If you look at the beginning, we've got a minus x cubed. So that tells me that it's got a sad ending. So it's looking something like that. So look at all the clues that we've had before from C1 to help us out with this. Now to find these coordinates, x is equal to 1, we pop that back into the original, so y is going to be equal to 2. We put x is equal to minus 1, put it back into the original equation, and y is equal to minus 2. So we've got two turning points, one at 1, 2, and the other at minus 1, minus 2. If we've to determine the nature, we will look at the second derivative, d2y by dx squared, and that's equal to minus 6x. So when x is equal to 1, the second derivative is equal to minus 6, which is less than 0, so that tells me that it's a maximum turning point. When x is equal to minus 1, the second derivative is equal to 6, which is greater than 0. So that tells me that it's a minimum turning point. So I guess you could have a bit of a sketch of this one. What would it look like? Probably something like that. So you've got a maximum at 1, 2 and a minimum at minus 1, minus 2. And I know it goes through 0 because if I put x equals 0, y equals 0, so it goes through there. We just have to find the roots of the other one. We weren't asked to sketch it, but it's quite useful to pull in all the other ideas that we've got from C1. Questions that I'd like you to do then, it's not on any pages there, is the next exercise on the next page, and you'll see that question 1, 2, 3, 5 and 7. Again, if you pause the video, have a go at these questions, and you'll see that on the next page. Those are the ones that I'd like you to do. So looking at 1, A, D and G, question 2, question 3, the first column, question 5 and question 7. So at the moment, if you could pause the video, have a go at the questions, and then I'll reveal the answers. Welcome back, and here are the solutions for you. So looking at question 1, can you check that you've got the correct answers there? I'll move onwards. So So on to the next page. And this is question 2. Can you notice for part B, it did ask for you to go a little bit before and a little bit after the turning point to find out what the gradient is, and you can see from there that you get a minimum turning point. You could have done the second derivative as well to see if it was greater than 0 or less than 0. So that's another 2 different ways of doing that one. And question 3. Now question 3, we had the second derivative was equal to 0. So that made it inconclusive. So I have to actually go a little bit before the turning point, a little bit after, find out the values of the gradient of the tangent to the curve, and then from there I can see that it's actually a minimum turning point. It's not a point of inflection, but it's a minimum turning point. E is very similar to what we did before. There's no values that make that equal to 0 because it's always positive. So watch out for points like that. And then question 3, I'll move over to the next page. You may want to pause it at that point. And next page, you can see that was question 3. And then moving on to question 5. Question 5 is very much like an exam question where you're given a cubic there. We'll look at it just before and after the turning point. So you can see we've got a point of inflection here. So positive gradient, stationary, which is horizontal line, and positive. So we've got a point of inflection at y equals x cubed. We know what that looks like. Then we state that we have got a point of inflection. B, we've got a to the power of 5. So we should have 4 turning points or thereabouts. Again, inconclusive. Then we've got a minimum and a maximum turning point. And then in part D, and then in question 7, again, same type of question as you would get in an exam, and you can see that it's asking for turning point, the y coordinate of it, if it's when is it an increasing function, and you can see that after x equals a half we've got an increasing function here, and then from there a decreasing function, and then a little sketch of it as well. So as well as being able to factorise it, completing the square as we did in C1, we can now apply differentiation to sketch our curves, whatever they may be. And then on the next page there's a summary of all the answers. That's the bare minimum that I gave you as ever, and if you wanted to do the ones in between, then you're welcome to do so. So we're going to take all these properties of stationary points, maximum, minimums, first derivative, second derivatives and so on, and we're going to combine it with brief situations where we've got manufacturing, it could be in, where you're making boxes and you want to try and maximise the amount of resources that you've got to make. So in this example here, we've got a large tank in the shape of a cuboid, and it's made from 54 metres squared of sheet metal. The tank has a horizontal base and no top. The height of the tank is x metres. 2 of the opposite vertical faces are squares. So if we translate that into what we have on a diagram, if the height is x and this is a square, so that front and the back of the tank is a square, and it's open as well, so it doesn't have a top, and we'll make y the depth of it. We're told the surface area, and we want to find out the volume. Now my advice here is, if in an exam situation you can't show this, then you still can go on and do parts B and C. So don't panic if you think, I haven't got a clue how to put this together, however I'm going to use it in parts B and C and pick up the marks there, then do that. So if we have a look at the surface area, we can form an equation from that, and then you should know the volume of a cuboid as well. So if we look at the volume of this cuboid is length times breadth times height, which is x squared y. And what we've got to do is make this into that equation there. Now if you look in part A, we don't have any y's in there. So that tells me that this y we're going to get from the surface area, hopefully. So if we look at the surface area, that is x squared, that is x squared, and each of these, the bottom there is going to be x times y, x times y, and x times y. So this whole surface area is equal to 54. So I can actually form an equation, hopefully get what y is, and then substitute it into the volume. So I'm going to call this volume equation 1, and I'm going to get the surface area is 54 is equal to 2 lots of x squared plus 3 lots of xy. And if I rearrange that, I get 3xy is equal to 2x, it's equal to 54 minus 2x squared. Y then is equal to 54 divided by 3 over x minus 2x squared divided by 3x. We can cancel that a little bit, and that becomes 18 over x minus 2x over 3. So if I now take this and sub it into 1, so I'm going to take this y, so this part here, and I'm going to sub it into here, and I should get this equation at the beginning in part A. So for part A then, v is equal to x squared, and y is 18 over x minus 2x over 3. If we multiply that out, we get 18x squared over x minus 2x cubed over 3, and that simplifies fully to 18x minus 2/3 x cubed, which was in part A, so I can say QED, I've managed to show it. Right, moving on to part B then. Given that x can vary, use differentiation to find the maximum minimum value of v. So if it varies, it can get bigger or smaller, but we are able to work out a maximum or a minimum. So if we work out dv by dx, so that's differentiating v with respect to x, because I've got x on this right hand side, then that becomes 18 minus 2x squared. And then for stationary values, it's equal to 0. So that's for stationary values. From that we can solve. So we get 2x squared is equal to 18. X squared is equal to 9. So x is equal to the square root of 9. And because we're dealing with a length, then we need that to be 3. It'll be 3 centimetres. So looking back at the question, given that x, use differentiation to find the maximum or minimum value of v. So we want Vmax, and Vmax happens when x is equal to 3, and we substitute it into the equation, so 18 times 3, and 2/3 times 3 cubed, and the maximum volume is 54 minus 18, which is 36 meters cubed. So we're just assuming that x gives us a maximum, but if we look back at the question, it says justify. So to justify it, we've got to look at our second derivative. So if we now look at d2v by dx squared, what we need to do is differentiate this again, and we get minus 4x, and when x is equal to 3, the second derivative is equal to minus 12, which is less than 0, so that implies that it must actually be a maximum volume. And these are typical exam questions that you'd be expected to formulate the algebra. As I said, if you can't do part A, don't worry about it. Assume that it's true and then use it in parts B and C. So you should be able to access the rest of the question. Right, moving on to example A. We have got an open box. So this open box is to be made from a rectangular sheet of card measuring 16 by 10 centimetres. 4 equal squares are to be cut from each corner. So what I've said there is I've got little x, we don't know what it is, but a square has been cut out of each corner. We make it into a tray. It's open top, so it has no lid. And what we want to do is find the length of the side of this square here, which makes the volume as large as possible. So as large as possible tells me that I'm looking for maximum, and then we've got to find the largest volume from that. So what I did was I took the surface area and I drew it into a three-dimensional box. And as you see, because we've got x taken away from both sides here, it would be 16 take away 2x would be the length of it. And then here we've got, altogether it was 10, but then we're taking 2x's away from it. So that would be the dimension of the open box. So if we look at the volume, we can work that out. We've been told that the volume has to be a maximum, basically, so we can get a value of x that will happen. So the volume is equal to the length times the breadth times the height. So that will give us the volume of the box. And then if we look at the stationary points, it will give us a value of x that will make this a maximum volume. Right, what we need to do is multiply this out. So take each term in turn. So I'll do the two brackets first of all. And then multiply it by the x. So the volume is 160x minus 52x squared plus 4x cubed. Now for stationary points, so that's going to be a maximum minimum, we have dv by dx is equal to 0. So if we differentiate, if we get dv by dx, it's going to be 160 minus 104x plus 12x squared. And we make that equal to 0. (104x plus 12x squared), and make that equal to 0. I'll make the numbers a little bit easier because I think we can divide through by 4 here. And if we do that, we get put it in order as well. We'll get 3x squared minus 26x plus 40 is equal to 0. I'm hoping that this is going to factorise, so we've got no option with the 3x squared, so it's got to be 3x and x, and the 40 is going to be 20 and 2, both the same signs, so we'll get x is equal to 20 upon 3, or x could be equal to 2. Now if we look at the 20 upon 3, it's about 6 and 2/3, but unfortunately if we sub that into this here, we would get a negative length, so that one's not actually valid. So we're looking at x equals 2 to give us a volume. So looking back at the question, it says find the length of the side of the square which makes the volume as large as possible. Right, let's see if this actually is a maximum. So we're going to have a look at the second derivative just to verify this. So the second derivative gives me minus 104 plus 24x, and at x equals 2, we'll substitute that in, and it'll give us minus 104 plus 48, which is less than 0, so indeed that is a maximum volume. And then we're going to work it out. The volume from the beginning was 60 minus 2x. I'll use the unsimplified one, and we'll put in x equals 2. So the volume is going to be 12 times 6 times 2. So the maximum volume, Vmax, is going to be 144 centimetres square cubed. And that, again, is another real-life example that we can apply differentiation. And these are the sorts of examples that or exam questions you get in C2 from that. Okay, what I would like you to do then, if you move to the bottom of this page, you will see on the next, well actually right, and the questions that I would like you to do are right, I don't seem to be able to find. We have the first question. Well, the first question where the farmer had a wall and had so much fencing to put round. Check your answers for that one, please. And then moving on, and what we have here, question 5, you can see that there. I'll move that up a little bit, so I've drawn the diagram. It helps. You need to know what the volume of a cylinder is as well, and the area of a circle, and the surface area of a cylinder. So all that comes in from GCSE. So check your work there. That was question 5, and then moving on to the last one, very similar to that last example that we had. Check your answers there. I'll move on to the next page for question 8, the remainder of it. And you can see there, the 3 1/3 is not valid. It will give you a negative length, so x is equal to 1, and pop that back in. Right, we have finished differentiation for C2, which is built on C1. And what I'd like you to do is the following questions. So we have, and this is to hand in on file paper. Question 1, this is absolute bare minimum again. If you want to do more, then I would thoroughly recommend it. So question 1 on the first page, and then 1 and 2 on the second page of questions. And then you you can give these a go as well. You won't be able to do that one just yet until we do integration at the end. So differentiation and integration can come at the same time in an exam question for C2. So I would say try and do as many of those as possible, hand in on file paper, and I'll get those marked for you.